Stanford University.
I'm Michelle Marinkovich, Associate Vice Provost for Undergraduate Education and Director of the Center for Teaching and Learning that you've no doubt noticed is sponsoring today's talk. I want to thank you so much for coming. This is actually the 101st talk in our award-winning Teachers on Teaching series. And as some of you know, we had the 100th talk last November in combination with the 35th anniversary celebration for CTL. And the Vice Provost for Undergraduate Education, Harry Elam, delivered then a wonderful lecture on whether the lecture was dead. Luckily, he concluded it wasn't, so you can look forward to a lecture today. But it is a wonderful lecture, and I just wanted to mention that there are many people who have seen it since it was delivered live, and it is available through a link on CTL's website. So I welcome you to look at it. And today, we're equally thrilled and honored that we have Professor Ralph Cohen, who is the Senior Associate Dean for the Sciences in the School of Humanities and Sciences, and who is also the Barbara Kimball Browning Professor in the Humanities and Sciences, and of course a Professor of Mathematics. And he's going to be talking to us on teaching freshman math and science to the masses, the challenges of designing and teaching service courses. This is a topic that we're just very grateful that he's been willing to address, since service courses often do not naturally arouse the passions of the faculty, but they can be extremely important in influencing students and even helping decide what they study and what kind of careers they pursue. And it's only when a service course is well done that it truly does serve the students. And Ralph is particularly qualified to speak on this topic, both as a mathematician and as a teacher. He received his bachelor's from the University of Michigan in mathematics in 1973. His master's in math from Brandeis in 75, and there's a trend starting here, his PhD in mathematics in 1978. But when you think of Ralph, don't just think of math, but of polymath, because his interests intersect other fields, K through 12 math, as well as the university level, and teaching and administration, as well as scholarship. His research, for example, in the areas of differential and algebraic topology intersects with some of the most theoretical work in physics, in quantum field and string theory. An outstanding scholar whose 60 articles and 4 books have brought him numerous awards, and I'd have to admit I was particularly attracted to the visiting professorships he's had in such enviable spots as Oxford and Cambridge, Princeton and the University of Paris. He won the H&S Dean's Award for Outstanding Teaching in 2002, and in 2010 was named the Gregory Amadon Fellow in Undergraduate Education. So this is clearly someone who can do both teaching and research at the highest levels. And although he was recognized for his work with undergraduates, he also has directed over 25 doctoral students and 12 postdocs. As I noted, though, he has paid attention to K through 12 mathematics and is even the co-founder of a summer camp for mathematics, bringing outstanding high school students to Stanford for the summer. He's also been a significant university citizen. He was chair of the math department from 92 to 95, served 2 terms in the faculty senate, directed the Mathematics Research Center here from 2000 to 2009, and as I noted, is also the Senior Associate Dean for the Sciences in the School of Humanities and Sciences. He's also played leading roles as an editor of just about every math journal worth looking at. So clearly this is a man who loves and has contributed to mathematics, mathematical education, academia, and he's the one to bring passion and insights into the topic of service courses. Thank you so much, Professor Ralph Cohen.
Thank you, Michelle. You can all hear me? I'm wired up properly? Good. Yeah, thank you. A very nice introduction. And I also, first of all, want to congratulate CTL on the 35th anniversary. I've known Michelle most of those 35 years, about 30 of them maybe. In particular, CTL does a terrific thing for the math department. It helps train our graduate student TAs as well as working with the undergraduates themselves, and it provides a great service. And I think also these lectures and the other forums that it provides for discussing teaching is an important thing too, because, I mean, after all, teaching undergraduates in particular is an important part of what we all do. And so it's good to have a forum in which we can discuss it in a serious way. I also wanted to thank, while I'm here, the VPUE's office. The Vice Provost for Undergraduate Education, Harry Elam, has been really supportive of freshman and sophomore level mathematics, as well as that level of science teaching as well. And so was his predecessor, John Brovman, and it has been really quite valuable, certainly to us in the math department. So what I'd like to talk about today is the experience of the math department in designing and redesigning the Math 50 series. So as many of you know, the Math 50 series is a sequence of 3 courses. There are 5-unit courses, primarily but not exclusively for freshmen. We designed it about 12 or 13 years ago initially. And we confronted a whole lot of issues. And my guess is, and you can correct me if I'm wrong, is that these issues are very similar to issues that come about in the designing of any large course, a large service course that consists primarily of students who will not major in the discipline of the course. How you get them interested, what kind of things do you emphasize in such a course? And in particular, when we were thinking about this course, we really had a whole bunch of goals. So it's interesting to look back to see how we did in those goals, and also just to discuss how we in the math department thought about those goals. So yeah, so let me talk about some of them. So as you know, many departments on campus need their students to have a solid background in mathematics. This has always been true of the sciences and engineering, computer science. But at the time, late 1990s, it was becoming increasingly true of some social science and humanities departments as well, like psychology and economics and linguistics. And we wanted to make sure that the students were getting the basic mathematical skills that they would need to be successful in these disciplines. That was sort of a primary importance. Making sure students learn specific skills contained in subjects such as linear algebra and calculus of several variables, differential equations, was and is quite an important part of what we do, and we want to try our best to get it right. And we knew this was a service course, and one of the most important services we provide is the introduction and development of mathematical skills for students. So skills is right up there at the top of the list. Now another issue or goal, which is related to skills but a little bit different, has to do with applications. As you all know, mathematics has a lot of applications in other fields, as I say, in the sciences and engineering, economics and the like. And we felt that it was important that students see problems or questions that arise in these different disciplines to which mathematics has something to say. That the skills they learn can be used to apply to problems in these disciplines. So thinking about problems in those disciplines was something that we wanted to describe to students. So I'll just call that applications. Another thing is simply problem solving. Of course, problem solving is one of the basic goals of mathematics in a variety of contexts. Of course, this is related to skills. It's related to applications as well. You need skills to solve the problem, skills in particular courses that are learned to solve problems. But on the other hand, there's a general mathematical perspective on problem solving that we wanted students to be exposed to and to come away with. And we wanted to make sure that they got an understanding that this mathematical perspective on problem solving would serve them well in other disciplines. One of the more difficult issues that we thought about in a serious way back then and continue to think about is the role of theory and proofs in a service course like this. And again, I think that this is most likely something that is confronted in any large service course where you're teaching students whose primary interests are not in that field. And so the question is, how much of the theory that's intrinsic to that field do you expose students to in a course like that? In our case, of course, this is a mathematics course. And even though it was primarily a service course, we felt that part of our role was to introduce mathematics as a discipline. Now, of course, every scientific discipline has its own method of verification of conjectures, of hypotheses. In a lab science, of course, that's done by experimental verification. In a social science, that's often done by conducting a study to verify hypotheses. But in mathematics, one states and proves precise theorems. And we wanted to expose students to that theory and to that point of view. So the real question arose, how much of this theory should we put into a course like this? Now, one complicating factor at the time, and it's still a complicating factor, so again, at the time was late 1990s, was that high school curricula were changing. High school math curricula were changing, and so students coming into Stanford had different backgrounds than they had before. And the curricula were changing even in the very best of schools. Schools that give students quite a few opportunities in mathematics and other subjects, such as taking calculus or statistics and offering courses that prepare them for advanced placement exams and that sort of thing. But what was happening is that the exposure to theory, the exposure to the concept of a proof in mathematics was really becoming a thing of the past in most high school curricula. You know, an important part of this, traditionally, many of you will have seen this, is the exposure to basic logic and deductive reasoning that one uses to prove geometry theorems, that typically in the middle of high school sometime. I remember getting a kick out of just learning the Latin names for some of these principles, modus ponens, modus tollens, and all of that. In fact, our own Pat Suppies from Stanford wrote a book on logic that was a real standard, still is, and was used in many high school curricula, including here in Palo Alto, as a way of preparing students for geometry and to prepare them for the deductive reasoning to do proofs. And many of you will remember that the notion of a column proof that you learn in 10th grade or 11th grade or something, where you take a piece of paper and fold it in half, so you have that line down the middle, and on the left side you write down an assertion, and on the right side you write down a justification for that assertion. Well, for better or worse, we found in the late 1990s that type of thing was happening less and less in high schools. In fact, in the mid-1990s, just a few years before that, the National Council of Teachers of Mathematics, which is the professional organization for secondary school math teachers, in the state of California, I'm sorry, this a national council, came up with a framework that explicitly called for a diminished role of proofs, and in fact, in certain circumstances, it called for the elimination of proofs in geometry curricula. And this became very controversial, as you can imagine, and it was one of the topics of the so-called math wars in the late 1990s, and that still persists today. On the one hand, you had so-called traditionalists, and on the other hand, you had people pushing a so-called reform movement, and it was really quite volatile and very high, done in a very public way, not necessarily in the best way, I think. But for better or worse, we were confronted with the issue that students, even the very best students, were being exposed to proofs very, very rarely. And so we had a question, how much should we expose them to proofs and to theory in general at the freshman level? And as I say, I view this as a special case of a more general question, that when designing a service course, no matter what subject really, how much of the theory that's intrinsic to that discipline should one expose students to in a service course? Another issue was simply teaching methodology, and I'll put technology, because we thought about those issues more or less at the same time. Should the courses be big lectures? Were there any choices to that? Should they be traditional blackboard talks? What should the role of technology be, both in the delivery of the lectures and in the content of the course itself? How do we use computers or calculators or whatever for actual problem solving, for actually helping to understand the subject matter itself? And as I say, what should the role of technology be in the design of the lectures? At that time, there were software packages, MATLAB and Mathematica and others, that were being developed and were quite useful. And what their role should be was a real question for us, and it's still a question. I think, in fact, that's one issue that the dust has not yet entirely settled on 12 or 13 years later. Yeah, and as I said before, my guess is that many of these types of issues, maybe not specifically that, but the types of issues arise in designing any large service course, particularly in the sciences. So I thought I'd spend some time telling you how we in the math department thought about these issues and how we, what decisions we made. And some of the decisions have changed over the years. So let me start by giving you some background. Since the 1960s, or perhaps even before that, Calculus 1, one variable calculus, has been the standard freshman level math course taught in most colleges and universities around the country. It still is in most places. Here at Stanford, we taught then, and we still teach, Math 41, beginning calculus. It's a two-course sequence, Math 41 and 2. And we teach a parallel sequence, the Math 19 sequence, which covers the same material, but in 3 quarters, so at a bit slower pace. And Math 41 in the fall, for example, was the math department's flagship course for many, many years. We had a professor of mathematics, I'm not sure when he came here, probably in the 40s, and he worked his entire career here. His main role was as a calculus instructor, Harold Bacon. Michelle will remember him. And he always taught these huge lectures, calculus, every single quarter. My conjecture was then, and I think still is that he probably holds the world's record for the most students seen by any one professor, having taught these large courses for at least 40 years. But starting, in the 70s, through the 70s anyway, calculus was only taught in a very small number of high schools. So it wasn't common through the 70s, I think, that Stanford students or any university students had seen much calculus. But that started to change in the 80s. I think it started to change because of the role advanced placement exams started to take. It became apparent that college and university admissions boards were using advanced placement tests as a measure of academic achievement and academic excellence. And so, courses that prepared students for advanced placement tests started blossoming all over the country, including calculus. And by the late 1980s, many, many students had seen calculus before. Many Stanford students had seen calculus before. And certainly by the mid-1990s, when we started thinking about these issues, the majority of Stanford freshmen had seen calculus before. Now, actually, I don't know the numbers, but if I were to guess, I would guess 90% of Stanford students have seen calculus before they came here, maybe even higher than that. But in particular, if I'm right and the numbers are anything like that, that includes many, many students who will not go on and major in math or physics or computer science, or the students from with interests all over the university. They come with a calculus background. And so by the late 80s, we were having the situation that our largest courses taught to freshmen, Math 41 and 19, were populated by many, many students who had seen the topics before. Not always in a terrific way. Many of the high school courses in calculus, left a lot to be desired. And the feeling at the time was, well, we should teach it right. And maybe we did. But it did involve some problems. And I think these problems exist actually throughout the freshman curriculum. So in my view, things weren't working so well at that time. What we did was, if a student came in with advanced placement credit, we placed them in what was called Math 43 at the time, beginning multivariable calculus. They placed out of Calculus 1. If they didn't do so well on the exam, or if they didn't take the exam, we had them start calculus over again. And I don't think it worked so well for a couple reasons. Stanford freshmen, especially in the fall quarter, they're really excited to start learning new things, to be exposed to new things. And I think it is an issue if, when they take their first fall term courses, the topics that they study are the same topics or a repeat of topics that they had in high school. Even if they learn it, and they do learn it in a much better or deeper way here, the fact that they've simply seen the topics before can cause some problems. I think it dampens enthusiasm sometimes. They're so anxious to learn new things and say, oh gosh, I'm going to take calculus all over again, or physics or chemistry or whatever it is. I'm going to do it all over again. And I think that is a problem that needs thought, especially as the university is considering its undergraduate curriculum again with the SUIS report. Again, being Stanford freshmen, chances are they received all A's in their high school, and in particular in their math courses. So there was a reasonable chance, in fact, a pretty good chance, that they'd take calculus, get an A in it in high school, then take calculus again here, same topics, taught better, taught more deeply, maybe more topics, do it much better than they do, but still roughly the same topics, and then they end up with a B or C. So in other words, they do it all over again and get a worse grade than they did when they started. And there are all sorts of reasons why that happens. The reasons are usually obvious, but I think many students found that pretty discouraging. And they'd come away thinking, oh, they hate math. Or worse than that, they'd come away thinking they're no good in math, and it would be discouraging for them to continue in a technical field where they needed math. And I think it was a problem, and frankly, we didn't know really how to address it. So that was happening. There were a couple of other things that were happening at the time, late 90s. One thing was calculators were everywhere. Every high school, every college, many universities, including Stanford, they were everywhere. We, at one point, in an experimental way, we spent a few years where we used calculators in our freshman courses. And I got to say, the TAs spent a whole lot of their time teaching the students how to use the calculator rather than using the calculators to do some real mathematics. And notice I said the TAs spent their time teaching the students, because I'm sure the faculty never quite figured it out anyway. And I must say, I had the view then, and still do, that Texas Instruments made hundreds of millions of dollars by convincing schools around the country, including colleges and universities, that it was important that they use their calculators in order to learn mathematics. And I haven't seen a serious study that shows that it's been particularly effective. But, oh, I should say, by the way, I should have said at the beginning, like these commercials and all that, the views that are expressed in this talk, they're just my views. They don't represent the math department. They don't represent humanities and sciences or anything. But more seriously at the time, as I mentioned before, really good software packages were being developed. MATLAB, Mathematica, and quite a few others. And we really wanted to think of the appropriate way to use that kind of software in the mathematics courses to enhance their mathematical learning. Another thing that was coming into play at the time was that some of the other departments, like computer science, maybe economics, were telling us that it was perhaps more important for their students to see early on linear algebra, maybe even statistics, maybe more important for them than seeing calculus right away. So there's a question about the order in which we teach things. At the time, linear algebra was a standalone course and was taught typically after the students had 3 or 4 quarters of calculus and analysis. And that was kind of ironic in some sense, because starting in the 3rd quarter, when you start doing calculus of several variables, boy, a bit of algebra sure would help. Linear algebra would help with that. In fact, at the time, and it's still a problem today, that because students in studying mathematics or calculus of several variables didn't have the basic algebra to work with, books were written and courses were given that restricted attention to 2 variables, or maybe 3 variables. And the actual calculations that were done were often very ad hoc and kind of messy, and also, frankly, misleading to the way both the mathematics, both intrinsically in mathematics, and also the way the mathematics was used. The differential equations, which was an important beginning course, a course that was quite important for engineers, for physicists, for in a variety of contexts, suffered from the same kind of problem. So it became clear to the math department that we needed to revamp the freshman curriculum to take into account that our freshmen had seen calculus before. But the real question was, given perhaps 1 quarter with these students, or maybe as much as 1 year, what do we teach them? And what topics do we teach them, from what perspective, and at what depth do we teach them, and how do we teach them? So we began in the math department with faculty meetings discussing this, and then we met with graduate students as well. A former student of mine, Mark, is here, who was a graduate student at the same time. And so we met with students who were TAs and get their take on it. And then we sponsored meetings with faculty from other departments, from science and engineering departments, economics, and to get their view on what they thought freshman mathematics should be to prepare for their disciplines. And of course, there wasn't a uniform opinion. There was no consensus gained, but it was really quite useful and quite interesting. Some people wanted us to go faster in the development of certain techniques. Some people wanted us to emphasize technology quite a bit more. But I remember being surprised that many people, maybe the majority of the people, felt that we should stress rigorous mathematical thinking in our courses. In other words, have students solve problems carefully and prove theorems. I think the view was that being good at problem solving in mathematics and being trained in rigorous thinking, the kind of rigorous thinking that's necessary to prove assertions and theorems, transfers well to other disciplines. After all, rigorous serious thinking is rigorous serious thinking. And whether it's applied to proving a theorem in mathematics, or whether it's applied to writing some complicated code in computer science, or whether it's applied to making a model of some economic system. And I personally found this pretty heartening. You know, there was not a call, in particular, there was not a call to water down the curriculum in order that students would feel more successful, whether they were or not, so that they would then have more confidence to go on to engineering or science or other disciplines. But rather, there was a call to offer students a serious and broad introduction to mathematics that would serve them well in these other disciplines. So at that point, the math department made what I think was really quite an important decision. Namely, it would develop a sequence of courses that was particularly geared to freshmen who had seen calculus before. And we knew that this would become our biggest course, our flagship course, if you would. Calculus 1, Math 41 and 19, would continue to be taught, and they'd continue to be important courses. But with the VPUE's help, actually, we were able to teach these courses using lecturers and teaching assistants, and that the faculty's attention in this level, freshman, sophomore, undergraduate mathematics, would then be focused on this multivariable mathematics that this new course would begin. And again, with their help, financial help, we were able to manage this. Again, the course was meant for students that had seen calculus before. We wanted students who succeeded on AP exams to take the course, but we didn't insist that they succeeded on AP exam. In other words, if a student saw calculus before and perhaps they didn't do well on the exam, or maybe didn't take it, or they're an international student so they wouldn't have taken it, but they felt they had a pretty good handle on their calculus background and they wanted to try this new course, they were allowed to do it, and still are. We knew it was a bit of a risk, but I think we felt that students would be well served by taking a math course in multivariable mathematics, which would be a subject that would be new to most students, and that by learning and doing this, which is in some sense a more advanced topic, they would be forced to recall and solidify their knowledge of the one variable calculus, the calculus they learned in high school. You know, it's often the case that the best way to solidify one's knowledge in a subject is, well, actually, probably the best way to solidify one's knowledge in a subject is to teach it. But failing that, often the best way to solidify your knowledge in a subject is to use it in something else, or to at least apply it in a more advanced topic. And I think we felt that this kind of idea would work in this case, that by teaching something new, multivariable calculus that required knowledge of one variable calculus, that would be at least as effective way of solidifying that knowledge as simply teaching it all over again to them. And I think this was actually proven to be the case for most of the students. Another decision we made at the time was to integrate the teaching of algebra, linear algebra, into the teaching of analysis. This might be special to the mathematics, but it was important, I think, that we realized that the needs of other departments were varied. And that was one thing. As I said before, some departments thought that seeing some algebra right away was really quite important. And we also thought, as I mentioned, that having that algebra available helped the mathematics, made it possible to learn multivariable calculus and differential equations in a more serious, effective way. So we wanted to integrate the algebra into the learning of the multivariable calculus and the differential equations. And this was actually, it's sort of such a natural idea, but it was a rather new idea at the time. Couldn't find textbooks that did it. We didn't know of any other colleges or universities that were teaching freshman mathematics in this way. And in particular, it was really difficult, and it's still difficult, to find appropriate textbooks from this perspective. But we pushed on and basically decided to develop this 3-course sequence that would teach students linear algebra, differential calculus of several variables, integral calculus of several variables, and differential equations, with the linear algebra integrated throughout. The goal was that a student coming into their freshman year with a calculus background could take this sequence of courses and end up with a good, solid math background that would be sufficient for most majors on campus and would be a good jumping off point for the more mathematical majors like physics or computer science, or majoring in mathematics or the math and computational science degree. Moreover, we wanted to start the course right away, first day, roll out of bed from your new dormitory room into the classroom, see some linear algebra right away. We wanted to teach something new to the students that very few of the students had seen before. It put everybody on the same level playing field, and it made good sense because, first of all, it's a topic that's interesting in its own right, and it's extremely applicable both within mathematics and to other disciplines. And in fact, we wanted to stress some of the applications, and in particular to computer science. And in fact, over the years, one of the interesting topics that's often discussed just a few weeks into the course is Sergey Brin's master's thesis that he did here at Stanford in the computer science department. In that thesis, he developed the page ranking algorithm that was then used by Google in their first search engine. And the content of the thesis involved linear algebra of the same sort students were learning in Math 51. And they enjoy it quite a bit to see how eigenvalues and eigenvectors were used in this way to develop a search engine for Google, which they're all very familiar with right away. So that was a nice thing. Another issue besides the applicability of linear algebra is that it lends itself to a discussion of mathematical theory and even philosophy. And this varies among the instructors who teach it, but we discuss with students how mathematics language is precise. We discuss how it's able to give precise definitions to concepts that they already have kind of a heuristic understanding of. For example, in algebra, the concepts of independence of variables or vectors and the concept of dimension, they all have a heuristic understanding of what dimensions mean, but we were able to make the language precise, and it was important for them to see that. Many students got a kick out of the fact that we could talk mathematically precise in a mathematically precise way about 20-dimensional spaces just as easily as you can talk about 2-dimensional or 3-dimensional spaces. They saw the geometric concepts that they were familiar with in 2 dimensions or 3 dimensions, like length and distance and angles, could be defined in a precise way in higher dimensions. And they also saw that it wasn't just fun and games, although I got to tell you, what's more fun than that? I mean, but they realized that being able to make precise various concepts had real value. Just the concept of independence, for example, just consider how many independent variables many economic systems have. Wouldn't it be good to know what you mean by independent variables when you say that? I mean, so the ability to take language that you kind of think you'll understand and make it precise is something that mathematics does, and it's something that exposure to that is quite useful for students to see. Also, you know, the fact that the subject involved new language and new definitions, it actually means that some of the theory and some of the proofs are a bit easier. And we saw that it was a way to introduce that. And in the course, right away, probably 3 weeks into the course, they're introduced to an important theorem that we call the rank nullity theorem. It's a theorem about linear transformations between vector spaces. But it's a real theorem, and they're responsible for the proof of it. And, you know, we were a little concerned in designing the course that maybe this theory wouldn't go over so well, that students would find it difficult, and some do. But, you know, most of the students do learn it. And a lot of them really get into it. And the deductive reasoning aspect that's required to understand proofs and to be able to write proofs really serves them well, and it's a perhaps surprising number of them really enjoy the exposure to that. And as I was saying before, for many of them, it was their first exposure to that. As I said before, finding the appropriate textbooks was really a problem. We tried a few over the first 2 or 3 years, and we weren't real happy with it. And then we put together what I think of as a Frankenstein textbook. We took bits of this textbook, bits of that textbook, bits of the third, and bound them all together, and we used that. And it worked okay, but there were some problems. You know, different textbooks might use different language or terminology, and that could be confusing. But then eventually, one of our star Zago assistant professors wrote some linear algebra notes. Stephen Lewandowski, and it was just a beautiful collection of notes they eventually published, and we used for our linear algebra aspect. And we sure need similar work like that one of our present Zagos has been working on, Joan Licata. So, but it was a problem at the beginning, and it's a continuing problem to find the appropriate textbooks written at this level. You know, as the course became more popular and more well-known, we were beginning to hear of several other universities that started to teach freshman mathematics in the same sort of way. Dartmouth, Johns Hopkins, Princeton all developed courses that were similar. And then textbook publishers started to introduce, for example, the integration of linear algebra into multivariable calculus. You now pick up a generic textbook on the subject, it will say something like linear algebra and multivariable calculus. 15 years ago, that wasn't the case. Most of these textbooks are still pretty crappy, in all honesty, but the very fact that they're thinking about doing that is a good thing. So another issue that confronted us at the time, that still confronts us, is the appropriate use of technology for the course. I mentioned our experience with calculators, and we didn't want an experience with more sophisticated software packages to be the same. Namely, we didn't want to design problems or homework sets in order to use the software. We wanted it to go the other way around. We wanted to demonstrate how the use of the software was important within mathematics, important in applications. And it's something that is still a work in progress. We've tried a variety of things with various levels of emphasis over years, and it's still an issue. We view that the using of computers to solve problems or to approximate solutions, and particularly understanding how they do it, what kind of algorithms the computers use, is really important within mathematics and also important in applications. So a related question is, how should technology be used in the actual delivery of lectures? We were chatting about this earlier. At a recent meeting of the International Congress of Mathematicians, so this is a congress that meets once every 4 years. It's the biggest mathematics conference in the world. It happens every 4 years. That's where they award the Fields Prize, which is mathematics' highest prize. At a recent meeting, David Mumford, who is a famous mathematician, in fact, a former Fields Prize winning mathematician, was giving a lecture. Now, Mumford he's from Brown University, and prior to that at Harvard University for many years. He was very famous for his work in the field of algebraic geometry, which is a field in pure mathematics. But in recent years, he's gotten interest in artificial intelligence and also the use of mathematics in neuroscience. So he was giving a lecture. And it was quite an impressive computer lecture with videos and sound and a light show and all the bells and whistles. And at some point he stopped and marveled at all this technology, and he was just sort of commenting on how useful technology had become for lectures, for giving lectures. And in fact, he said, it's become almost as good as a blackboard and chalk. And I got to say, I was all prepared to give a blackboard talk today. In fact, when Michelle and David asked me what my technology needs were, I got a kick out of that, actually, that expression. Lots of technology needs. But David described this room and what kind of technology support it could have and all these things. But it didn't have a blackboard. But they were very kind and offered to wheel one in for me. Then I went and hurt my shoulder playing tennis recently. And so now I can't write on the blackboard above about this high. So certainly one of the advantages of computer-based talks over blackboards is much easier on sore shoulders, that's for sure. But seriously, there are a lot of advantages. In particular, in a computer-based talk, whether it's PowerPoint or whatever it is, it's an electronic thing. It can be saved as a file that is available for students, put on a website. Students have access to it. And there are technologically more sophisticated methods like prepackaged video type lectures, or we were discussing earlier about forms where you have small modules, 10 or 15-minute videos on a particular topic that have links to literature or textbooks on the topic and that sort of thing. And it's all very good and useful. But I can't help, and again, this is my own personal view, I can't help but think that it removes a real benefit of Blackboard talks. Namely, in a Blackboard talk, students see the instructors working mathematics or whatever the subject. The process slows down in that setting, and that's a good thing. Plus, the students take notes, their own notes with pen and paper in this setting, as opposed to having lecture notes available to them on a website that were already prepared. And I believe that the physical aspect of taking notes is a very useful educational tool. Learning mathematics, like learning sciences, is a slow process. It's a process that I think requires having a pen and paper nearby. In fact, most mathematicians that I know read mathematics with a pen and paper nearby, and they use it to, when they read something, an assertion or a calculation, to kind of work it out themselves, to work out the details themselves or do the calculations themselves. So they come away with understanding it in a much better and deeper way. Reading mathematics or science is not like reading novels, and many freshmen have never been exposed to that in a serious way. And that was one thing we wanted to do. But also being exposed to an instructor working mathematics slowly on a blackboard while they're taking notes, having to study their own notes at home to prepare for the course, we thought had value along these same lines. I'm concerned a little bit that having a course based around computer-based lectures, or even more so, these prepackaged lectures, where the materials are all made available to them, takes away the process, or can take away the process, of seeing someone work out the mathematics, taking notes, and slowly working things out for themselves to gain a real understanding. Now, at a recent meeting of science chairs that I organize in my job in the dean's office, we were talking about teaching. Harry Elam, from the vice provost for undergraduate education, was at the meeting, and Robin was at the meeting, and we were talking about teaching, and I kind of expressed this view that Blackboard Talks still had value, and I said, well, this is my own old fuddy-duddy perspective on this. And Bob Simoni, who's the chair of the biology department, responded by saying, you know, that's not just an old fuddy-duddy perspective, but that's the perspective from the age of the dinosaurs. And, you know, of course he's right. But I can't help but think that it might be good to pause in the rush to use technology and online methods for delivering lectures to see if we're losing something along the way. I guess that's my real point. Not that online lectures don't have their place, but we just need to think about what's being gained and what's being lost. We were also confronted with the issue of pedagogy. Do we teach from a heuristic point of view that does not emphasize precision or rigor? And as I said, this was the view of the so-called reform movement at the time. And it wasn't just a movement in K-12 mathematics. Many colleges and universities, some of our competitors, top research universities, were designing courses with this perspective and this view. And we rejected the view because we thought it was important to gain a balance between mathematical theory on the one hand and problem solving and skills and applications on the other. But what amused me about the discussion was the idea that the reform movement was something new. In fact, if you go and look in the education literature, education schools have been debating this kind of thing since the beginning of education schools more than 100 years ago. And in fact, 50 years ago, well, I couldn't resist showing you a video from 50 years ago. And the video is of Tom Lehrer discussing what at the time was called new math. And the concept of new 50 years ago is the same as the concept of new that's being used today. And by the way, if you don't know of Tom Lehrer, get to know of Tom Lehrer. He was absolutely terrific. He was a political and social satirist in the late 50s and early 60s. He did his satire to music. He was a writer. Some of you may remember an old TV show called That Was the Week That Was. He was a writer for that TV show. It was kind of a precursor to The Daily Show or something like that. It was really terrific. And he was a mathematician. He had a PhD in mathematics from Harvard, and he spent a long career just down the road at UC Santa Cruz in the math department there. So if I can work my technology, I will show to you Tom Lehrer and his bit from the early 1960s, nearly 50 years ago, on new math. And for those of you who are familiar with it or have seen it before, I was going to apologize, but you'll probably enjoy it again anyway. So here it is.
Some of you who have small children may have perhaps been put in the embarrassing position of being unable to do your child's arithmetic homework because of the current revolution in mathematics teaching known as the new math. So as a public service here tonight, I thought I would offer a brief lesson in the new math tonight. We're going to cover subtraction. This is the first room I've worked for a while. It didn't have a blackboard, so we will have to make do with more primitive visual aids, as they say in the ed biz. Consider the following subtraction problem, which I will put up here. 342 minus 173. Now, remember how we used to do that. 3 from 2 is 9, carry the 1, and if you're under 35 or went to a private school, you say 7 from 3 is 6, but if you're over 35 and went to a public school, you say 8 from 4 is 6. And carry the 1, so we have 169. But in the new approach, as you know, the important thing is to understand what you're doing rather than to get the right answer. Here's how they do it now. You can't take 3 from 2. 2 is less than 3, so you look at the 4 in the tens place. Now that's really 4 tens, so you make it 3 tens, regroup, and you change a 10 to 10 ones, and you add to the 2 and get 12, and you take away 3, that's 9. Is that clear? Now instead of 4 in the tens place, you've got 3 because you added 1, that is to say 10 to the 2, but you can't take 7 from 3, so you look in the hundreds place. From the 3 you then use 1 to make 10 ones, and you know why 4 plus minus 1 plus 10 is 14 minus 1, because addition is commutative, right? And so you got 13 tens, and you take away 7, and that leaves 5. Well, 6 actually, but the idea is the important thing. Now go back to the hundreds place. You're left with 2, and you take away 1 from 2, and that leaves... Everybody get 1? Not bad for the first day. Hooray for new math, new math. It won't do you a bit of good to review math. It's so simple, so very simple, that only a child can do it. Now that actually is not the answer that I had in mind, because the book that I got this problem out of wants you to do it in base 8. But don't panic. Base 8 is just like base 10, really, if you're missing 2 fingers. Shall we have a go at it? Hang on. You can't take 3 from 2. 2 is less than 3, so you look at the 4 in the 8's place. Now that's really 4 8s, so you make it 3 8s, regroup, and you change an 8 to 8 ones, and you add to the 2, and you get 1 2 base 8, which is 10 base 10, and you take away 3, that's 7. Okay? Now instead of 4 in the 8's place, you've got 3 because you added 1, that is to say 8, to the 2, but you can't take 7 from 3, so you look at the 64s. 64. How did 64 get into it? I hear you cry. Well, 64 is 8 squared, don't you see? Well, you ask a silly question, you get a silly answer. From the 3, you then use 1 to make 8 ones. You add those ones to the 3, and you get 1 3 base 8, or in other words, in base 10, you have 11, and you take away 7, and 7 from 11 is 4. Now go back to the 64s. You're left with 2, and you take away 1 from 2, and that leaves... Now, let's not always see the same hands. One, that's right. Whoever got 1 can stay after the show and clean the erasers. Hooray for new math, new math. It won't do you a bit of good to review math. It's so simple, so very simple, that only a child can do it. Come back tomorrow night. We're gonna do fractions.
Well, needless to say, I can't follow Tom Lehrer very well. But suffice it to say that even though we're in iTunes here, you can listen to some music if you like. You know, even though the Math 50 sequence is definitely still a work in progress, I think it's been quite successful over the last 10 or 12 years. The enrollment is high. For example, more than 2 out of every 3 Stanford freshmen take Math 51, many of whom take it in the fall quarter. And that's a full 10 units beyond the general education requirement in mathematics. That's very impressive, I think. 2 out of 3 students go that far in mathematics, and many go much further. In fact, the general enrollment in math courses overall has been quite high over the last few years. And the number of majors and minors in math and computational sciences has had dramatic increases. And of course, there are many factors in this, including we in the math department hired a terrific cadre of young people over the last several years who are, besides being outstanding mathematicians, are terrific teachers. But I can't help but the success of the 50 series has had something to do with it too. Now, for many years, I think, as I understand it, the most popular course, the largest course on campus, was this course called Sleep and Dreams that was taught by Professor William Dement, who's a very famous professor of psychiatry in the medical school. And now Math 51 is one of the more popular courses. I don't know if it's the largest or not, but it's one of the more popular courses on campus. And so I guess I guess one could say the reason is that the students found that they could accomplish their sleeping and dreaming in a math class just as well as, okay. Anyway, I think I'll end here. It's been a real pleasure, and I really want to thank you again for this opportunity. Thank you. Sure. Yeah.
You talked a little bit about the goals that you people have with making this new math course, and a little bit about what kind of pedagogies you used in class and so on. What did you do with the assessments?
What did we do with them?
Yeah, did you change that? Did you also try to implement any changes in that? Purely technical changes, more?
Right, I don't know if y'all heard it, but the question was, were there changes in the student assessments, I take it? In all honesty, no. We use the standard student evaluation. There was a lot of discussion with students, and in fact, one thing I didn't say, part of this course, we had quite a bit of tutoring available to students, some of it by the TAs, some of it, of course, here in CTL, but also SUMO, the Stanford Undergraduate Math Organization, the organization of math majors, started giving informal evening sessions. And so there was a certain amount of feedback from the students in the course through the undergraduate math majors as they met them that way. But it was quite informal.
Yeah, that's my question. I didn't phrase it right. The testing of the students. So, what kind of problem sets, finals, did they change?
Yeah, they did. The testing, I mean, the simple answer is the tests matched the curriculum. So they were responsible for the techniques they learned and the skills they learned. They were responsible for solving problems, and they were responsible for some theory, some proofs as well. It was a challenge on the homeworks because the homeworks oftentimes come from books, and the books were a problem. So it's a continuing problem, and I think it still is, actually.
So I took the whole 50 series and quite enjoyed it for the most part. It did seem somewhat rote, at least when compared to some of like CS theory courses, for example. And I think your point about wanting to see something new was excellent, because this was certainly part of it. I enjoyed seeing some problem where at first glance I had no idea how to solve it. And CS would be like, here is this thing, and we're not even going to tell you what paradigm it fits into, but kind of solve it. And so I was wondering, kind of in that vein, how difficult it would be to teach something like from Polio or Zeitz, a like very problem-solving type approach.
Yeah, I personally like that approach, to sort of structure the course around solving problems. And I think that's what the Polio method ultimately is about. It's not so difficult. I mean, it's not so easy, I should say. One of the difficulties is just having the appropriate textbook to do that, or appropriate materials to do that. I should say also that there is a certain amount of doing that. I mean, the weekly problem sets and the exams and all, much of them are simply solving problems. And it really is oriented around that. But we didn't want that to be the only thing, or even necessarily the primary thing. It's certainly an important part of it, but it wasn't the whole story. As I was trying to say, we really had to balance several things, including problem solving. Yeah?
The university has gone through several models of undergraduate advising for undeclared students, volunteers and professors with honorariums, and now sort of the two advisors. But from the point of view of students arriving in mathematics, can you see any difference?
So the question was about freshman advising primarily. I think freshman advising is still a work in progress in this university, and I think particularly as far with respect to mathematics, it doesn't work so well often. one often hears that advice from advisors that, oh, you've taken an AP exam or you've had a bunch of math in your background, so why don't you take a year off of mathematics, do other things, and then if you get interested again your sophomore year, you can do that. Well, you know, there's some aspect of mathematics that's kind of like a sport. You know, if you don't do it for a year, you're going to be out of practice, and you're going to be rusty, and you're going to be in worse shape than you were to begin with. My own view is that the basic foundation of freshman advising is fine, but when it comes down to the nitty-gritty of what course should I take for my background, they should come to the department. They should go to the math department, go to the physics department, go to the chemistry department, talk to the faculty who teach the courses. Having it done in the dorms by people who aren't particularly familiar with it often leads to some bad advice. Yeah. Oh.
And I would say that we definitely encourage students to go to the faculty advising, especially
Good, good.
to talk through what they're looking for and then decide on the course.
Very good, good. Peter.
Yeah. This is a question that's probably not, it may be relevant to the Math 50 series, but it's certainly something I've encountered in the Physics 40 series, 20 series in particular, and that is the broad range of diversity of preparation the students taking the course. And you find, you know, it always surprises me that it's just as large as it is. And I'm wondering how you deal with that.
It's a tough problem, but one of the things was, like I mentioned, the introduction of linear algebra right from the start, because that was a topic, and again, it may not be relevant in physics, but it's a topic that most of the students, whatever their background been, it's a topic that most of them hadn't seen before. So it did tend to put people on a level playing field. But, you know, some students are better prepared than others. And there's, you know, so we focused on the curriculum. And Stanford students have an amazing capacity to adapt. That the, you know, weaker ones that are the ones with weaker backgrounds have ways, and we gave the resources, tutoring and such things to help them fill in their background if necessary. But we focused on the curriculum, so long as, I mean, we had to keep our eyes on the students as well, just make sure there wasn't a disconnect there. But, you know, you're right, it is an issue, and I don't know how to solve that issue. But I do think that starting with a topic that's new to everybody is really helpful. I don't know if you can do that in a beginning physics course or not. I don't know. Start with string theory. There you go. Yeah. Good, good.
For more, please visit us at stanford.edu.